Welcome to a sim code. If you want to stay on top of your coding game, like this video and subscribe to get more tips and tricks. Let's talk about binary trees. Alright, so what's a binary tree? Think of it as a structure where each node has two potential children, a left child and a right child. The first node in the tree is called the root, and every other node in the tree will either have 0, 1, or 2 children. Imagine a tree where each branch splits into two smaller branches, left and right, creating a tree-like shape. And that's the essence of a binary tree. Include the standard input-output library for printing to the console. Include the standard library to handle memory allocation, malloc, and program control, exit. So, how do we represent that in code? We define a node in the tree using a struct, which is like a blueprint for our node. Here's the struct for a binary tree node. Data stores the actual value of the node. Think of it as the content of the node. Left is a pointer to the left child node. It will be null if there is no left child. Right is a pointer to the right child node. It will be null if there is no right child. Let's write code to create a new node. Now that we know how a node is structured, let's talk about creating one. When we create a node, we allocate some memory for it, set its data value, and set its left and right pointers to null, because a new node starts as a leaf node with no children. This is done using the newNode function. First up, we need to allocate memory for the new node. Malloc is used here to request memory from the system. We need enough space to store an integer, the data, and two pointers, left and right. But what if malloc fails? If there is no enough memory available, it will return null. So, it is always a good practice to check if malloc worked or not. If malloc fails, we simply print an error message and stop the program using exit 1. Show error message if malloc fails. Terminate the program because we cannot continue without memory. Now that we have memory, let's initialize the node. The data field gets the value that was passed to the function. This is the value we want to store in our node. At this point, the node does not have any children, so we set both the left and right child pointers to null. Finally, we return the pointer to the newly created node. This allows us to attach this node somewhere in our tree later. Time to traverse the tree. Let's explore pre-order traversal. Now, let's talk about traversing the tree. Traversal means visiting each node in a particular order. There are several types of tree traversal methods, and one of the most common is pre-order traversal. In pre-order, we visit the nodes in this order. First, let's check if we have reached the end of a branch. If root is null, it means we have no node to visit, so we simply return and do nothing. This is our base case. For recursion, it prevents the function from going further down a non-existent path. If the current node is null, just stop and go back. Visit the root node. We are at the root, so let's print its value. The data field of the current node contains the value we want to display. Print the node's value. Move to the left subtree. We recursively call the preorder function on the left child of the current node. This is like saying, okay, now lead a euro s explore the left side before moving to the right. Move to the right subtree. After finishing the left subtree, we recursively call preorder for the right child. This is where the right side of the tree gets explored. Inner traversal, visiting left, root, right. Another common traversal is called inner traversal. In inner, the nodes are visited in this order. It's super useful when we want the values to be printed in ascending order for a binary search tree, BST. Same as before, check if we have reached the end of a branch. First, explore the left child, left subtree. Once the left subtree is done, we visit the root. Now, print the data of the current node. Print the node's value. Finally, explore the right child, right subtree. Post-order traversal. Left, right. Root post-order traversal works the opposite of pre-order. Here, we visit the nodes in this order. Post-order traversal is often used when we need to process children before their parent, such as in delete operations. Base case if we have reached a null node. Stop the recursion. Explore the left subtree. Explore the right subtree. Finally, visit the root. Print the node's value. Main function lets test everything. Let's create the root node of our tree. We will start with a value of 1. This creates a node with value 1. Now let's build the rest of the tree. Add a left child with value 2. Add a right child with value 3. Let's add more nodes to make the tree bigger. Left child of node 2. Right child of node 2. Left child of node 3. Right child of node 3. Now let's test our tree with different traversals. Should print 1, 2, 4, 5, 3, 6, 7. Should print 4, 2, 5, 1, 6, 3, 7. Should print 4, 5, 2, 6, 7, 3, 1. Now run our code. If you enjoyed the video, please like, comment, and make sure to subscribe.